Alright. Hallo zusammen. Danke für den warmen Empfang. Ich freue mich hier zu sein. Mein Deutsch ist leider nicht so gut, also geht's auf in English weiter. If I talk too fast, please just tell me to slow down. So, my name is Rich Harris, and this talk is called Fine-Grained Everything. I'm here representing a project called Svelte, which apparently some of you have heard of. For those of you who are not familiar, Svelte is a declarative component framework similar in spirit to React or Solid or Vue, things of that nature, albeit with a few philosophical differences. And in addition to Svelte itself, we have a full-stack application meta-framework called Svelte Kit, which is our vision for what building robust, accessible web apps should feel like. It is an incomplete vision. We have a lot of work still to do, and some of that work is what I'm here to talk about today. If you haven't tried Svelte before, you should. It's a project that many of your fellow developers are very excited about. This is the State of JavaScript survey. Svelte was the most interesting front-end framework for the last 6 years running. I know that a lot of people here at Lotum are fans of Vue.js, and that's okay. Nobody's perfect. I've been working on the project for 9 years at this point. It started with an idea. What if we could have a declarative component framework like React, but instead of doing all the work in the browser, we could build a compiler that did as much of the work as possible at build time. But we really came onto the scene in 2019 when we launched Svelte 3, and I presented the idea at a conference called You Gotta Love Frontend. And this clip gives you some idea of why we didn't like the React way of doing things.
Virtual DOM is regenerated each time, and then React's job is to reconcile what came before with what came after. So let's see what this process looks like. First, we look at the top-level element. It was a div, it's still a div, so we keep it. Then we need to look at the attributes. It had a class name, app. It still has a class name, app, so we keep it. Then we look at the children. It had an H1. It still has an H1, so we keep it. Then we look what's inside the H1. Some text. It hasn't changed. We keep it. Look at the input. It's still an input. We keep it. The value hasn't changed. We keep it. Look at a button. It's still a button. We keep it. Its text has changed, so we need to apply that to the DOM. All that work to change a 4 to a 5. As engineers, we should be offended at all that inefficiency, but that's not the bad part. The bad part is that we keep running this code over and over again. Every time there is any state change at all, we need to redeclare these functions that close over that local state.
He's right. A lot of that talk holds up pretty well. The front-end world has largely come around to the idea that React is one of the slower and bulkier ways to update the DOM. Back then, you would hear people say things like, React is fast because it has a virtual DOM. And nowadays, people understand that React's performance is good enough most of the time, despite the virtual DOM. But as soon as you need to move a lot of pixels at 60 frames per second, you're probably going to have to start doing manual optimizations. The idea of running your code again and again and again is rightly seen as being very inefficient. But you don't need to take my word for it. You can just ask the React team. Earlier this month, they shipped version 1.0 of the React compiler, which auto-memoizes your component code precisely to avoid rerunning it more often than it needs to. I consider this the ultimate vindication of our ideas. But there are also some things that we got wrong. Firstly, we overestimated what you could do with a compiler. Unless you have some incredibly sophisticated static analysis, it's hard to know which actions will affect which state and which state will result in which DOM updates. Compiler-driven reactivity is much faster than the traditional React approach, but it breaks down when you try to make changes to objects and arrays, because if, for example, you toggle the property of an individual to-do, you have to invalidate the entire to-dos array, checking to see if any of the other values have changed. And so in recent years, a new consensus has emerged, mostly thanks to this guy. This is Ryan Carniato, the creator of Solid, and one of the kindest and most authentic people in web development. His whole deal is that the way to achieve optimal performance is with fine-grained reactivity. The idea is that you model your data using something called signals, each of which represents an atomic value. And when those signal values change, we know exactly which updates need to happen. Svelte 5 was released a year ago, and we're fully on board with this program. We use signals with our compiler to make fine-grained reactivity automatic, but in a way that feels like using normal JavaScript values. So our previous example becomes this. We declare the to-dos array as state, using the special syntax we call a rune, and Svelte creates signals for the properties inside it. Now, when we toggle or edit, nothing else needs to care about it. That's fine-grained reactivity. There's another more fundamental thing that we got wrong, though. Like every framework, we've always been fixated on how fast you can update the DOM. And fine-grained reactivity is just the latest chapter of that. At this point, we can all declare victory. The gap between signal-powered reactivity and what you can achieve with low-level DOM updates that you write by hand is small enough that there's really not much left to do. Rendering and reactivity are solved problems, and this is why every new framework released in the last few years has failed to gain any traction at all, except for Astro, which cleverly focused on a very different set of problems. All the while, React was working on something else. The biggest performance problem they saw was not the DOM, it was the data. Data is not a solved problem. When you build a web app, you're building a distributed system in which a small computer on an often flaky network has to communicate with a bunch of different servers. If you're building a client-side single-page app, it might look something like this. The user requests a page, which results in an empty HTML shell delivered from a CDN somewhere near the user. The HTML imports your app's CSS and JavaScript. Those JS and CSS files might import other JS and CSS files, and they don't do anything until they're all loaded. Once they're loaded, we can start the app. But before we can actually show anything to the user, we probably need to get some data. So the user makes a request to your server. This time, the request can't be handled by a CDN because the response is personalized. So it needs to go all the way to your origin server, which could be a long way from the user. The origin server then needs to consult a database, hopefully within the same data center. Once it has that, it can respond with the data. And based on that response, the app might need to get more data. And this is pretty common during initialization. Now, mobile devices these days are generally quite powerful, but latency is still a real problem. So when you have these waterfalls, it tends to result in a really janky user experience. Server-side rendering goes a long way towards fixing this. If you use a framework with SSR, like SvelteKit, then the HTML response will have done most of the work already. You have content for the user to look at. You'll have link elements that preload all the JS and CSS assets that you're about to import. And the response will contain the initial data so that we can turn it into an interactive client-side app without needing to go back to the server. For static content, you can even pre-render the HTML at build time and put it on a CDN so that it's close to the user. There's a common misconception that you only need SSR if you care about search engine optimization. And this is wrong. SSR is about performance and resilience. If you care about performance, if you care about your users, then SSR is not optional. It is absolutely essential. But it's also not the complete solution because it only affects the first load. What the React team found was that in many apps, one of two things will happen. Either components load data independently of each other, in which case you experience loading spinners popping in and out like a game of whack-a-mole, or you load data sequentially as you're rendering the new page and start hitting those dreaded waterfalls again. And so the way that React would have us solve this is with something called server components. And so let's take a look at what that looks like in the context of a Next app, which is the most common way to use RSCs today. OK, so we have three files that matter in this demo. We have page.tsx, which tells Next when the user hits the root page, render this content. And we have account.ts, which contains some server-side data and some actions for retrieving and updating that data. And then finally, we have this button component, which obviously represents the big red square in the middle. Now, in a real app, you would have a database here. You wouldn't just be yeeting stuff into memory, but for the purposes of illustration, this will do. You'll notice that we have this use server directive here, which tells Next that this stuff will only ever run on the server, whereas the button has use client because it is a client component. It does render on the server, but it is a client component which allows it to have interactivity. And you might think, well, can't we just put this markup inside our page? And the answer is no, because in order for a component to respond to user events, it needs to be a client component. Now, I am a React skeptic, but I actually think this is extremely cool. With these three files, we have a button that can read and write server state, and it's type safe. We know that get count is a number. And it's all wired up automatically. We're not having to deal with JSON serialization and deserialization. We're not calling fetch ourselves. And it's all synchronized and organized in a very nice way. But there are some parts of this that I don't like. I think the server-client component split is objectively confusing. Like, you can't have state and event handlers in your server-side components, but you can't read data directly inside your client components. And if you want to combine logic, you have to learn some very complicated rules for how to combine all of those things. Like, think about how you would make optimistic updates, because here, there's a bit of a delay when I push the button. It's a simulated delay, because we're simulating a slow network. But that's a real issue that you will face, and you kind of want to have an optimistic update as soon as the button is clicked. How would you do that? You can do it, but it will take you most of the day. It's complicated. And so the consensus among a lot of developers, at least the ones that I've talked to, is that it's just too difficult. Ultimately, though, that's just about education and experience. My real concern is something more fundamental. If we look at the network tab, as we're interacting with this app, and we push the button, you'll see that we're fetching some data from the server. And if we inspect that payload, we can see what's inside it. Is all of this stuff. It doesn't just contain the data that changed. It contains all of the static content on the page as well. Loads and loads and loads of stuff here. And that's because the server is stateless. It doesn't know what the client already has, so it has to rerun the entire thing and send it all back to the client. So each of those clicks results in 5 kilobytes of data. Now, in production, it compresses down a little bit. It's not quite that bad. But this is the flaw. This is the most basic page you can imagine. If your page had more content on it, then that payload would increase, even as the actual data that's being transferred is the same. All that work just to change a 4 to a 5. As engineers, we should be offended at all that inefficiency. But that's not the bad part. The bad part is that we're rerunning this code over and over again. We're doing extra computation on servers that you're paying for, and we're sending more data to the user than they actually need. So on the Svelte team, we've been eagerly following all this work and the overall trends that are happening in the front-end world. But instead of copying them, we went back to first principles and asked ourselves, what problems are we really trying to solve here? And can we come up with solutions that have a better set of trade-offs, that take advantage of Svelte's unique capabilities as a compiler? And the problem is this. First, we want components to be able to manage their own data requirements. Historically, front-end frameworks have dealt with data by loading it outside the rendering process and passing it into components in the form of props. But that's a really limiting approach with a lot of problems. In the same way that components manage their dependencies on styles and JavaScript modules and other components and so on, a component that can get its own data is much more useful than one that can't. Secondly, asynchronous work should be coordinated. If you have two separate components that get data independently of each other in response to the same user interaction, you almost always want them to update simultaneously, even if one gets its data first. We've all seen websites with loading spinners that pop in and out all over the place. And it's a really horrible user experience. It's very hard for independent components to manage this stuff amongst themselves, so it becomes the framework's job, our job, to coordinate everything. Thirdly, we want real type safety. In 2025, it's not enough to just get a blob of JSON anymore. Programmers expect to get type checking and autocomplete and inline documentation when you hover over things in your editor. But beyond that, when you're passing data between the client and the server, you need to have guarantees that the data that you're getting is in the right shape and that your function isn't being called by an out-of-date client that's been left open for a while, or worse, by hackers trying to mine Bitcoin on your computer. Validation is really important. Fourth, it should be dead simple to use. No awkward constraints about putting your reads in server components and your writes in client components. No rules about where you can do async work. Something I believe very deeply is that computers should work for us, not the other way around. And finally, we want it to be fast. We want to eliminate waterfalls. We want to anticipate the user's needs by getting data exactly when they need it. We want to minimize the amount of work that needs to happen, both in the browser and on the server. We want tiny payloads, not ginormous blobs of JSON. In other words, we don't just want fine-grained reactivity, we want fine-grained everything. And so for the last year, we've gone deep on this problem, like really deep. And we think we've come up with something that's significantly better than our competitors. It comes in two parts. Async Svelte is the foundation. It lets you use await inside your components in a way that is automatically parallelized and coordinated. And on top of that, there's a new feature in SvelteKit called remote functions. So you know what time it is? It is time for a controlled demo. I'm going to quit the next app and move over to the Svelte equivalent. All right. When I push the button, the count goes up. I know, hold your applause. All right, let's see what's going on here. So right now, it's just using some client-side state. I'm cheating. And so if I refresh the page, it goes away. That's obviously no good. We want to have the state on the server. So the first thing we're going to do is put some state in a file that is only going to run on the server. In here, I have a module called count.remote.ts. In SvelteKit, when you have a module that has .remote in the file name, that guarantees that that will always run on the server. So it's a safe place to access environment variables and things like that. And we can expose things from the server to the client in a safe and efficient way. So inside count.remote.ts, do let count equals 0. And then I'm going to expose it with a getCount function. In SvelteKit, we call this a query. GetCount equals query. Then we just return count, like so. And then back in our page component, I can replace these occurrences of count with await getCount. All right, and so it's now pulling data from the server, although if I push the button, nothing now happens. Excuse me. Now you might look at this and think, hang on a minute, this is a bit of a rookie mistake. We've got await count followed by await count. If there's one thing we know as JavaScript programmers, it's that when you have sequential awaits, that means that you're going to be doing the work sequentially. So we're going to go to the network, get our data, bring it back, and then we're immediately going to go back to the network to get the data again. That seems a bit silly. Well, it actually works okay in Svelte for two reasons. Number one, we know that everything inside the component is a pure expression. It's not having any side effects. So it's okay to run all these things in parallel. The compiler will automatically do promise.all on your await expressions. And secondly, in SvelteKit, remote functions are cached because it points to the same resource. We know that it's the same data that we're getting each time, and so the client is able to keep that in memory for as long as it's used on screen. So it's okay to do this. We could hoist it out and put it in the script, but we don't need to. All right, let's wire it up. Let's, inside here, instead of count plus equals 1, we now need to do an increment. And the way that we do that is with the opposite of a query, which is a command. Count plus equals 1. But maybe we don't want to increment by 1. Maybe we want to increment by more than 1. So if we want to pass data from the client to the server, we need to validate it. I'm going to import a validation library called Valibot. I don't know if anyone's familiar with Valibot. It's similar to Zod, but a little smaller. I prefer it, but you can use anything as long as it adheres to something called standard schema, which is a way of ensuring that multiple validation libraries can all be used by different frameworks. So we'll say v.number, and then inside here, this is now typed correctly as a number. We'll do count plus equals d. Then back over here, instead of count plus equals 1, we'll do increment. And then we'll just pass in 1. If I push the button, nothing happens. That's because SvelteKit doesn't know what needs to update as a result of that action taking place. So go back over here. Inside this increment function, we're going to grab the query and refresh it. And so now when we push the button, you can see that we are getting payloads that are not 5 kilobytes or even 2 kilobytes. It's 0.3 kilobytes, and the content of that is just this. It contains the information that the result succeeded, along with any data that was refreshed as a result. So it happens in a single request. We're not committing the action, waiting for that to complete, and then getting the data. It all happens in what we call a single flight mutation. So it's pretty efficient. What happens, though, if we have a slow network? What happens if I make this an async function and sleep for a second? It's a pretty unsatisfying user experience. And there's a few things that we could do here. We could, back in our page, we could detect that the command is pending. We have a handy little increment.pending property that we could use. Or we could do pending plus equals 1 here, and then pending minus equals 1 afterwards, and then we've got to worry about error handling and so on. So we can actually do something a little bit different. Because this is a very simple state change, like we kind of know what data to expect back from the server. You can imagine like this is a like button on a tweet or something like this. The server is the source of truth, but we can guess what it's going to tell us. And we can do that here by saying that this increment call updates our getCount query with an override. We'll pass in the current value, and we'll return the next value. And so now when we push it, it updates immediately. And you can see that the network activity is happening in the background. And if some of these requests were to fail, if math.random is less than 0.5, throw new error. Oh no. Now, it will get the optimistic update, but any that fail will automatically roll back. And because they're applied as functions, instead of just updating the state directly, it's able to surgically remove them from the stack as they fail. Let's do a different demo. Let's go over to our weather demo. All right, you see it's raining in London, as usual. You see that there's no network activity on page load, even though we have some data from our weather API. It's not actually doing any network stuff because this is server-side rendered. So if we look inside the HTML, we will see the data that is powering these components. But if I toggle open one of these other cities, we will get some more data. Now, if I were to click this Show All button, maybe I'll put the thing on the side so we can see them all. Then I have 3 more cities in my list. You could imagine that I could have many more. It's going to result in 3 more fetches. It's loading from an external API, which is always the downfall of live demos. Oh no, something went wrong. Let's try that again. Okay, so it's done 3 more fetches to get the data. And we get the automatic coordination, right? So we do the 3 fetches, but they don't update as the data comes back. They update all in one go. But it's still not totally ideal that we're doing 3 separate network requests. It's not terrible. Like HTTP2 means that you can do that, and it's not that costly. But on the back end, you receive those requests separately, and you issue 3 separate requests to the external API. And each of your API calls counts towards your monthly limit. It's not something that you really want to do. And so you might look at this and think, this is why React server components were invented, because it's all happening in one go. I can get all the data in one go. And that's true up to a point. You would have to manage the batching yourself, which is not totally straightforward, but it can be done. But then there's another problem that you've created for yourselves. Remember we talked about the difference between server and client components. If I have some client-side state, like I want to be able to toggle between Celsius and Fahrenheit, I've been living in the US so long that I speak Fahrenheit now, although it probably doesn't make sense to most people here. If you're doing this with server components, then you've got to find a way to get that client state into your server components. Like you don't want to render that on the server. You don't want to have to go back every time you toggle this. And that's kind of difficult. It's doable, but it's another one of those challenges where you have to remember the rules of composition. And personally, I don't have time for that nonsense. So wouldn't it be nicer if we could have the best of both worlds? We can have client-side state, but we can also have batched requests. And the good news is, of course, we can. So I bring open the component where this is all happening. And we can see that this forecast component down here is pulling data from this getForecast remote function, which is pulling the data from an external API and just returning it as it is. And at the moment, it's doing one at a time. And we can convert this into a batch query by adding batch here. And this time, we keep the exact same schema as before, but instead of getting an individual city, we're going to get a bunch of cities. And instead of getting one thing at a time, we'll pass them all to the API. And instead of returning that data, we'll return a function that, given a city, returns the data that we just received. So if I did this correctly, then this time, I load Paris, that's one request. And when I click Show All, it's another single request. A little bit larger, 3 kilobytes, because it's got 3 cities instead of just one, but it's all happening in one go. Thank you. All right, one last demo before I get back to my slides. You've all seen a to-do app, right? Everyone's familiar with a to-do app? Okay. Have you seen the sequel to do to do? All right, so who here in their job as a web developer, who here deals with forms? Who here in their job as a web developer likes working with forms? All right, not many people. Forms do kind of suck. They're very hard to get right. And we are hoping that we can make it at least a little bit nicer. All right, so we have a login/register form down here that expects an email address and a password. If I bring up the logic for this, we can see how that's implemented. This form element has a login object that has been spread onto it. That login object has method equals post. It has the action that the data is going to be posted to. And it has event handlers that handle the submission if JavaScript is available. If I command click on that, we can see how it's implemented. So just like query and command, this is a remote function that lives in a remote file called auth.remote.ts. And once again, we're passing in a schema that defines the shape of our form. We have an email, which has some constraints. We have a password, which has some constraints. And then the action can either be login or register. Once the data has passed validation, it will flow through to the handler, where we can actually commit the action. And so with each of these fields, we can spread them onto an input element to wire it up automatically. And we get lots of nice type safety. Login fields dot auto-completes with the fields that are defined by our form, which makes it easy to get things right. And if there are any errors, we can print those too, along with having the correct ARIA attribute so that people who are using your app via a screen reader and other assistive technologies can also find out when something's gone wrong. So if I try and log in here, and I do the wrong password, I get the information that the password is incorrect using the validation constraint that I had already applied. It's nice and straightforward. Okay, we'll clear it out. All right, so now I have another form. I have a form for creating a to-do, and this one has a slightly more complicated schema. This time, instead of just having top-level properties, we have text, and then we have a nested attributes object, and this time, one of those properties is a number that corresponds to the slider down here. So if I were to add some things with different priorities, You can see them added to the form. And this all works without JavaScript because we're using regular forms. And what's nice is that, again, I get good type safety. Because we know that this is a numeric input, it will make sure that I am creating this input as either a number or a range, because it's going to be turned into a numeric value. And directly beneath it, I can get a live view of the data that has been inputted into the form. So if I drag the slider, you can see the text next to it updates immediately. And obviously, I can toggle these by creation date and so on. It's a little bit slow if I try and toggle these, though. So let's investigate. See what's going on with that. So this toggle is coming from here, toggle to do, which is a remote form. And inside here, you can see the offending await sleep. Someone left that in there just to make our lives more difficult. And we could just get rid of it and make things fast again, but it's more interesting to fix it on the front end, because you are going to have to deal with slow networks from time to time. So let's do that. We'll take our toggle form and we will enhance it with some client-side logic. We will call submit. And just like before with our command, we can say updates, get to-dos with an override. It gets the current to-dos and it replaces them with a mapped version. Return, I've got to remember how to do this. T, and then done is going to be the opposite of t.done. Sorry, if t equals to do, the opposite of to do.done, otherwise t.done. I think this will work. Let's find out. Okay, so somewhere along the way, I've done this incorrectly. Live demos are a hell of a drug. Okay, if t equals to do, return t, otherwise return. Probably should have practiced this before I came on stage, shouldn't I? Okay, well, here's one I made earlier. I can toggle these, and again, if I open the network tab to show you what's happening, the network activity is rolling along in the background, and as it resolves, the front end will just remove the override that's there in favor of the new canonical data from the server. So you get the best of both worlds. You get data that lives on the server and is guaranteed to be correct, but you also get immediate user feedback. All right, I'm going to go back to my slides then. So does this mean that forms are fun now? No. Forms will never be fun. But at least now you can spend a little bit less time building the damn things. So as we've been building all this stuff, we've encountered some really interesting challenges. And I think we've made some pretty novel contributions. I'll give you 2 examples that we shipped just this week. The first is something that we call forking. When a user is navigating around your app, they'll touch or hover over a link for a couple of hundred milliseconds before the click event is registered. If they're on a mobile device, the screen will register the touchdown before the click event is fired. And we can use that time to start fetching the data that the user is about to need, because we can have a high degree of confidence that they're about to navigate. But if the data dependencies are all inside the components, we need to render those components to figure out what they are, and we can't show the components until we know for a fact that the user wants to navigate. So instead, we can apply the change inside a fork. And if the user does navigate, we can commit the fork. And if they don't navigate, then we can discard it. You can have as many simultaneous forks as you need, along with as many overlapping async state changes as the user can generate, and they will all be cleanly merged together as they resolve. Kind of like merging Git branches, but without the possibility of merge conflicts. And typically, you won't use this API yourself. It's done for you by SvelteKit. So we have a little demo here. Here we've got the three wise monkeys. As I navigate around the app, when I select one of the monkeys, it's going to fetch some data, or at least simulate fetching some data with a set timeout. And then it's going to show it down here with await render monkey. If I click on one of these, you'll see that 500 millisecond delay. But if I hover over it for a minute first, which tends to happen, and then I click on it, the data is ready. The fork has already been generated, and it's ready to commit as soon as it goes. And what's interesting about this implementation is that we only render this thing once, exactly once. Once it's there, it's done, and we don't need to do it again. That's fine-grained everything. Now, to pull this off, to avoid needing to regenerate that content every time you click on one of these links, is something that I think you can only do if you have both a fine-grained signal graph and a compiler. So I think the reason that we're the first people to do this is that we are the only people who can do this. I look forward to being proved wrong. Another trick that's really difficult to pull off is out-of-order rendering. Imagine you have a component that gets some data and renders a child component that also gets some data. For example, you might have a blog post where the main component gets the blog post data, but it also includes a comments component that handles the comments. In React, you would get the blog post data, and then you would render the child component. Right? It's just how it works. Code runs from top to bottom. And if you want to avoid that, you have to come up with sophisticated preloading strategies, which makes everything more tightly coupled. You can't just make changes to the comments component or delete it altogether without having an impact on your preloading code. But Svelte is different because we're a compiler. And the compiler can see that that comments component doesn't depend on the post data. So rather than running the code from top to bottom, it can render individual parts of your app eagerly so that everything is available sooner. And then once the data is ready, we can render the rest of it. There's nothing that you, the developer, need to do to make this work. The computer is working for you and not the other way around. There are still some unsolved problems. We have a caching API, automatic refreshing, syncing between tabs, streaming file uploads, real-time streaming, and so on. We have some designs around this stuff that I'm really excited about. But these are all solvable problems that we'll get to soon. Okay. I've been quite critical of React during this talk, so I think I should clarify that, if anything, I am a React fan. I think the team has some of the smartest minds in web development doing some of the most interesting work, and so I want to take a moment to defend them. Because yes, compared to Svelte's fine-grained everything, React server component payloads are a little bit bulky. But you know what's even more extravagant? Getting an entirely new document every time you click on a link, even though most of the content and assets are the same. Take Astro, for example. Wait, did he say Astro? I was with him when he was talking shit about React, but Astro, like, they're the good guys, aren't they? Well, yeah, they are good guys and gals. And I mentioned them earlier as the one new framework in the last 5 years that has made an impact because they have focused on developer needs like content management that has kind of been overlooked by the rest of us. And everybody loves Astro. I love Astro. Just like React, it is built by friendly, dedicated people who are committed to improving the open web. There are lots of great reasons to use Astro. It is feature-rich. It is easy to use. It has a great community. It works really well with Svelte. Performance is not one of those reasons. I know, right? Surprise Pikachu face. Performance is one of the things that Astro is known for. It ships 0 kilobytes of JavaScript by default. It says so right on the homepage. But you know what? 0 kilobytes of JavaScript is not a feature. Lighthouse scores are not a feature. The feature is how it feels to use the app. And as we've seen in this talk, we can use JavaScript to make apps feel faster by being more intentional about the work that we do. Because this isn't really about Astro, it's about the category of website that is designed for building, namely MPAs or multi-page apps. Astro is just the best implementation of that idea. When you click on a link in an MPA, the browser has a lot of work to do. It has to go to the server to get some fresh HTML, which is usually mostly the same as the current document. It has to unload the existing document from memory, parse the new one, looking for hints that it's going to need to start loading other resources. And then it needs to go and get all of those as well. Often those resources will live in the cache, so they can be reused, but they still need to be parsed and evaluated. If you have ads or analytics or things like that, and you probably do, then they need to run all over again. Multi-page apps are expensive, but they feel cheap. Even the best engineers' MPAs have a kind of stickiness to them, where you click a link and there's a perceptible delay before anything happens, even if you're using link rel equals prefetch. And often there'll be flashes of scroll bars and fonts that are reloading and so on. This is Astro's own doc site on a simulated 4G connection, and this is a good, well-designed, well-engineered site with excellent content. This is about as good as MPAs get. And this is the SvelteKit doc site, which is roughly comparable in terms of complexity. And this time, the gap between clicking on a link and seeing the result is shorter because the browser has so much less work to do. All it does is fetch a small data payload and then update the middle of the page. That's fine-grained everything. So of course it's going to be faster. There's an unfortunate mentality in web performance circles that the platform is the only thing you need to learn, and anything that's layered between you and it is inherently detrimental to user experience. And it is true that there is no shortage of bad SPAs to use as evidence. But ultimately, it's a myth. We can do better. Used well, modern JavaScript frameworks can make web apps that are richer, faster, more accessible, and more delightful. Automatic caching, preloading, parallel fetches, granular updates, optimistic UI, validating client-server communication, and all of the other things that we've covered are fiendishly difficult to do well by hand. So if you're someone that believes that JavaScript was a mistake, hang on to your skepticism. Demand the best from your tools. But I hope that this talk has given you a reason to examine that idea more closely. Thank you.